All right, so we now like to dive into the analysis of this algorithm. And to do that, we're going to sort of first build up some intuition and then just write down the proof. Okay, so at each step, we're getting something from the exponential mechanism, some index IT, such that this inner product is close to what it should be, right? So, or ideally, like close to something like the error of the current iterate, okay, the current estimate we have. All right, now suppose that the algorithm like just stank completely, like, and suppose that the error of PT always remained high. Okay, so let's say suppose it's high at all capital T time steps. Okay, let's say at least some number alpha. Then if we look at the regret of the algorithm, the regret of the exponential mechanism over the course of the multiplicative weights algorithm over the course of its execution, then it's going to look something like this. It's going to be, the regret, recall, is sorry, I'm fix my notation here. So T, PT. We're going to look at the regret relative to a specific distribution, namely H sub x, the actual distribution H sub x. So we're going to look at the regret relative to H. So that looks like this. Okay, and now that's the same as the average over time steps of the cost of PT minus applied to PT minus H. And what we assumed is that that we were getting something that approximates the exponential mechanism was actually doing its job and giving us something that approximates this error alpha. So what we're getting is like very, very roughly 1 over T times something that's at least alpha at each stage. Okay, and so that means we're actually getting a regret. The overall average regret is something like alpha. On the other hand, the regret bound, the theorem that we started with, implies that this regret is at most 2 log m over square root of t. And so what does that mean? It means that like t can't actually be very big, like, or alternatively, alpha can't be very big. Okay, so if the error is at least alpha at all time steps, then in fact that error is at most about 1 over square root of t. Okay, and this is the connection to regret of an online algorithm that is the key to the analysis of this procedure. All right, so like, what can we conclude here? Well, there are a few ways to think about it, but one way to think about it is, well, then t can't be very big. T can be at most like log m over alpha squared. Now we get to pick t, so we're going to pick t to be like, bigger than that, like, big enough. And so in particular, this, when t is large, the average error will be small. And that's exactly what we want. Okay, so let's try to formalize that a little more carefully. To formalize things, we need to formalize both privacy and accuracy. So let's start with privacy, because in some sense that's an easier place to start. So this algorithm that we're looking at, it's a composition, an adaptive indeed composition of T algorithms, each of which is epsilon naught differentially private. Okay. So that means that it's MWEM is epsilon delta differentially private for epsilon, which by the strong composition theorem is 2t log 1 over delta plus t times epsilon naught e to the epsilon naught minus 1. I'm just writing out the theorem we had, so that this is, this is the strong composition from lecture 7 or so, 7, 8, 9, I don't remember. 10? I don't remember the lecture number. And so what do we, we're not going to fight for the constants today because that's going to be too much work. So instead, we're just going to get rough asymptotics, but this is about epsilon naught times square root of t times log 1 over delta, at least when when we're in the regime where the final epsilon is less than 1. Okay. So that's the regime we're going to work in, just because it makes our math and lives a little easier. And so one way, the way we're going to sort of flip this around. So if I write epsilon naught as a function of epsilon, what I get is something like, so it's about epsilon over square root of t log 1 over delta. And I'm going to write that as 1 over some constant involving epsilon delta, which has the form we've been using so far. So square root of, now c epsilon delta is square root of log 1 over delta over epsilon times square root of t. Okay, so that's it for the privacy analysis. Okay, well, what about accuracy? So in order to talk about accuracy, we first have to try to get our hands on what the exponential mechanism does. So we analyze the exponential mechanism in lecture 6. And what that shows is the following, is that with probability at least 1 minus beta over t, each individual execution of, so beta here is just some parameter that we'll set later, but it's just our, like, the failure probability of the algorithm as a whole. So each execution of the exponential mechanism satisfies the following, that it's going to pick a query phi I with the following property. It'll be at least the error, which is the maximum possible score of PT, right? So remember, we said that the error was the maximum score of any query. And so the algorithm, the exponential mechanism, gives us something with error, which is close to that, where close is measured by the log of the number of things we're selecting among, times the failure probability, times 1 over the failure probability. So in this case, that's t over beta divided by epsilon naught n. And so we're not going to worry about the exact form too much, but like, we're going to just call this thing, this quantity here, we're going to call that like alpha naught. Okay. The log t over beta, the t over beta term is actually going to turn out not to be very important, but the log k is going to show up. That's going to stick with us, and of course the n in the denominator is going to be super useful. All right, so how do we where do we go from here? Well, let's analyze the error of our final estimate. So remember the error of p hat. That is so that's the maximum over I of phi I of p hat minus x. Okay. All right. So remember that p hat is the average of all the iterates we produced over the course of the algorithm. And that's good. That's fine here because this function that we're this error function, it's actually convex. So it's actually a convex function of p hat because it's a maximum of convex functions of linear functions, which happen to also, everything linear is also convex. So actually, one of the in-class exercises from the lecture where we discussed gradient descent asked you to show that the maximum of a bunch of convex functions is itself convex. Okay, so why is that useful? Well, that allows us to apply Jensen's inequality, and it shows us that the following, that is at most the average. The Jensen's inequality says the value of a convex function evaluated on the average is at most the average of the evaluations of the function. So that what we get is now the errors of p, here I'll put it in red so it's easier to see, pt. Okay, so what we've done is we've taken this error function and evaluated it on each of the individual distributions we came up with over the course of the algorithm. And this is, this connection is due to the step we can do by Jensen's inequality. Okay, and that's just a generic fact about convex functions. Okay, so why is this useful? Well, the thing we've written here, this is the error of pt. Okay, and so we can apply the our accuracy statement for the exponential mechanism. So with probability 1 minus beta, all of the executions of the exponential mechanism did exactly what they were supposed to and satisfied this guarantee. So at this part, we're going to have to say, like, this part is with probability at least 1 minus beta by a union bound. What we get is for each of these executions, exactly the right thing. So CT times P17 minus HS. And now just plus alpha naught. So each of these is sort of within alpha naught of what it's supposed to be. Okay. All right. So so this allowed us to, so this was just, this is the only part where we're kind of making a probabilistic statement, is as long as the exponential mechanism is doing exactly what it's supposed to, we're good. All right, so let's now apply the, let's try and set things up so we can apply the regret theorem, the same analysis we did kind of sketched out a few minutes ago. So now we're going to just rewrite this as the sum of CT PT minus the average of CT times H. We've still got the alpha 0. Notice the alpha 0 gets added up t times, but then divided by t, so that comes out in the wash. And then the point is that this is my regret. Okay, and so that can't be very big. And now so that's the first term. And now let's plug in what we know about alpha naught. So alpha naught is, some constant. The constants really don't matter. So we get k times t over beta. divided by n and divided by epsilon naught, and epsilon naught, so I'm just going to sort of do the substitution here. So I'm going to replace epsilon naught by its actual value, which, if you recall, was about 1 over square root of t. Okay, so I'm just going to plug that in down here. And what we get is square root of t over, times c epsilon delta, and the whole thing divided by n. Okay, so at this point, we're doing pretty well. We can now choose the t we want. Okay, and to choose t, we're going to ignore the log part, the t that shows up in the log, because it won't really change our asymptotics all that much. And so what we really want is to balance. We've got like this 1 over square root of t here and this square root of t here. And so we're going to choose square root of t to balance these two terms as closely, and make them about the same. And so like the natural way to do that is to set t. So I'm going to set t to like make these two terms essentially the same. So it will be log of m times square root of n over square root of log of k t over beta times c. All right, and then what we'll get is sort of up to some big O, up to some constant. We'll get like basically when you balance terms, you wind up getting the geometric average of like the two things you're balancing out. So in this case, we'll get log to the 1/4 of m times log to the 1/2 of k over beta, and I'm going to ignore the t because it turns out not to really matter too much. Okay, because it's asymptotically going to be like less than usually in the k. But yeah, I'm being a little sloppy. There really should be a log m term that I'm not gonna worry too much about. Okay. And then we get square root of n in the denominator and c epsilon delta out front. Okay, and it turns out that's my final alpha. Okay, so this is when we sort of plug in the right value of t, this is what we get. And so what can we conclude? We get that the error of p hat is going to be at most alpha with probability at least 1 minus beta when n is sufficiently large. And how big does n have to be? Well, to figure that out, I'll just reorganize this equation. I'll take this square root of n and swap it with the alpha, put alpha underneath it and square, and what we'll get is big O and dropping the log m term of c. Sorry, let me rewrite this a little different. So this c should have had a square root on it. So when one of the funny things about these algorithms is when you isolate alpha, you get this, like the error term, you get this kind of very complicated expressions that are with lots of roots and stuff that are hard to interpret. But if you sort of isolate n and look at like how big does n have to be to get a given level of alpha, then you get much cleaner expressions that are easier to understand. So what we get is c log of k over beta times square root of log of m, all divided by alpha squared, as promised. Okay, and this is an O tilde expression, which means I've dropped some log terms in this case. Okay. And I just did that for readability. And we're all done. So what we've proven is that this algorithm gives this nice error guarantee when the sample size is sufficiently large. And so, QED. And so let's go back up and review everything we did. If we scroll all the way back up to the top, what did we get? We got this guarantee that we have here, which is that, we get this much better dependency on the number. We get an L infinity error guarantee, so all the queries are going to be right. And the dependency on the number of queries we're concerned with is much better than it is on the Gaussian mechanism. And the dependency on the number of the size of the universe now has been introduced. And really, like, again, I'll just reiterate what I said before, that you should think of log m as some sort of measure of dimensionality of the data. Okay, so this is giving us some sense of how complex the data records are. And so what we've done is at the expense of introducing a dependency on this data dimension, we've now got a much better dependency on the number of queries, and that's a win. Okay, I'll see you guys in class.